Hi everyone, welcome back. For the next part of our series, we're going to be looking at how to apply some of the graphical skills that we learned in the previous section to derive some equations by which we can henceforth use algebraic means in order to study motion. So for some motivating questions, have you ever been driving towards a stoplight showing green when it turns yellow and you think, do I have enough room to slow down and stop? Or can I maintain my speed and make it actually through the light? Or if I speed up too much, will the cops catch me? So, how about if a penny was dropped off the top of the Empire State Building, would it be going fast enough to kill somebody when it reaches the ground? In fact, the latter part of that was dealt with in a Mythbusters episode, which you might be familiar with. So we're going to consider these questions and a lot more throughout this unit. So, in this unit, we are going to essentially begin working with word problems. In other words, most physics problems that you're ever going to have to deal with are actually word problems. And becoming better at physics involves becoming better at word problems and applying skills for solving word problems. So, in addition to writing down your givens, one of the big points in solving these word problems is to break them up into simple chunks. These simple chunks will allow us to identify some givens that might not have necessarily stood out to us to begin with. And then we're going to work with these formulas that technically are vectors. In other words, they have a magnitude and a direction. Now for this non-AP class, we're going to be considering the vector nature simply in terms of the fact that position, displacement, velocity, and acceleration can be either positive or negative. And we will often denote the rightward direction as positive and the leftward direction as negative. And using these formulas, we are going to relate displacement, velocity, and acceleration, along with the time coordinate, to concrete situations. Now, a big assumption that we're going to be working with throughout this unit is that the acceleration is constant. In other words, jerk is equal to 0. And this is not only going to simplify the problems, but also allow us to come up with just a few equations which will apply to a wide variety of circumstances. So how do we recognize what our givens are in a problem? In a lot of situations, you can figure that out just by the units. For example, position, which is symbolized by the symbol x, has units of distance, and examples of those might be centimeters, miles, inches, light years, and meters, for example, as well as lots of other things, feet, etc. Time is going to have time units. Symbol for time is lowercase t, and time units might include minutes, years, milliseconds, fortnights, seconds, etc. Velocity, though, velocity, remember, is the slope of a position versus time graph. In other words, it's going to have the same units that a slope of position versus time would have. In other words, vertical units divided by horizontal units. So that'll be distance units divided by time units, meaning things like centimeters per second, miles per hour, really any combination of the first row, any combination of taking something in the first row and dividing by something in the second row. How about acceleration? Well, acceleration is the rate at which velocity changes. In other words, the slope of a velocity versus time graph. So that'll be velocity units divided by time units. But velocity units are distance units over time units. So acceleration must be distance units over time units divided by time units, which is distance units over 2 factors of time units. So that would be a combination of anything in the first row divided by 2 of anything in the second row. And it's okay to repeat things. In fact, most often you will repeat things. For example, the SI unit for acceleration is meters per square second, where you've taken meters over seconds per second. In fact, that has a specific meaning that we're going to get to later. So the other SI units include meters, seconds, and meters per second. Those are the SI base units for position and time, meters and seconds, and velocity and acceleration are going to be variations thereof. As we're going to get to throughout the rest of this course, there are other SI units as well. In fact, the 3 main base SI units are meters for position, seconds for time, and kilograms for mass, but we'll encounter how to deal with mass in the next unit. So a simple rule of thumb that always works when solving problems with the equations that we're about to encounter is that whenever you have physical quantities that are in weird combinations of units like feet, miles, years, etc., just convert everything to SI units. That will often save you a lot of time. Once you become more advanced physics students, then you can determine, like, okay, when do I need to convert, when do I not need to convert, and just allow everything to work out in cancellation. But for now, just concentrate on converting things to SI units and then solving. So again, technically what we're going to be dealing with are vector equations, but we are generally going to suppress the vector nature and just consider the fact that position, velocity, acceleration, displacement can either be positive or negative. So let me show you the formulae first, and then we'll see how to get these. The first equation. Well, the first part of the first equation is something that you already knew. Displacement is final position minus initial position. So before, we would often use subscripts for initial and final, with I being initial and F being final. Here we're going to drop that and simply say that 0 denotes the initial whatever, whether it's position, velocity, etc. And lack of a subscript denotes final. Now, we see that not only is displacement just final position minus initial position, but if you assume acceleration is constant, which we are, then displacement apparently is equal to v naught times t plus 1/2 at squared. And notice that you can often find it useful to rearrange this. If something started off with a non-zero initial position, then we just add the x naught to both sides and say that x equals x naught plus v naught t plus 1/2 at squared. So this is an equation you should definitely memorize. V equals v naught plus at. In other words, final velocity is equal to initial velocity plus acceleration times time. Well, you know back from studying graphs that acceleration is the rate at which position changes. So delta v over delta t is equal to a. So apparently a being delta v over delta t, you can just rearrange and say that delta v is equal to a times t. Well, move the v naught back to the other side, you have v minus v naught. That is delta v equals a times t, where here I'm replacing t with delta t or delta t with t. They are often interchangeable because the vast majority of the time we're going to start at t equals 0. If that's not the case, then sometimes you have to be careful and remind yourself that, hey, in all of these equations, the t's are actually technically delta t's. Now, with a little bit of algebraic trickery, you can solve this second equation in terms of t and plug it back into the t in the first equation and rearrange. And after you have rearranged, you will obtain that v squared is equal to v naught squared plus 2a delta x. In other words, final velocity squared equals initial velocity squared plus 2a delta x. And when we say v naught, we're talking about the subscript 0, which is often called naught, especially when it's used as a subscript, and AUGHT literally means nothing, but like all for naught, but v naught is just initial velocity. It doesn't mean it's 0. If it was 0, we wouldn't be writing it, but just the velocity at time 0. And finally, the fourth equation, you should recognize this back from our graphical stuff. Average velocity is displacement over time. But if the acceleration is constant, how can you figure out the average velocity, say, along a line segment? Well, take the 2 points on the line segment for their velocities, add them together, and divide them by 2. Just the average of 2 numbers. So, again, that only works if acceleration is constant. Although, the first part of this set of equalities, v averages delta x over delta t, is true regardless, because that's the definition of average velocity. So, just a reminder what these symbols mean. X naught is initial position, v naught is initial velocity, x is final position, v is final velocity, a is acceleration, and v average is the average velocity along a path. That v average equation is most often useful when taking the second part of this equality and rearranging for something, like maybe saying that final velocity is equal to 2 delta x over delta t minus v naught. If you're given v naught, delta x, and delta t. Now let's see how we can actually derive these equations from our graphical kinematics skills. So let's consider this graph. Here we have an acceleration versus time graph. And notice I've renamed my axes because it's usually kind of bad practice to give the same name to your axes as the name that you are given to particular points on that axis. So I've renamed my axes and just put primes on them. Don't even think about taking derivatives. That's not what these primes mean. So an acceleration versus time graph, and remember we're saying acceleration is constant in the rest of this unit. So if it's constant, that means on an A versus T graph, it's just going to be a flat line. That's what this green horizontal line is. It's the acceleration versus time, quote, curve for our motion. So okay, well, remember that taking the area under an acceleration versus time graph gives you the change in velocity, just as taking the area under a velocity versus time graph gives you the change in position. And that's because, after all, acceleration is the rate at which velocity changes, so the total velocity change is equal to just acceleration times time, or you can think of it as average acceleration times time, which would be found by taking the area under your graph, and the times time is already dealt with in taking the area. So, well, what's the area of this? That's the area of a rectangle. What's the area of a rectangle? It's base times height. The base is t, the height is a, so I'm going to rearrange that and say that the area is a times t. Well, remember the area under an acceleration versus time graph is the change in velocity. So apparently change in velocity is a times t. Well, change in velocity is just called v minus v naught, final minus initial. So v minus v naught is at, so I'll just add v naught to both sides and say v equals v naught plus at. That is one of the equations that we should memorize. So again, all we did is we took the area under a constant acceleration versus time graph. Now, again, we already kind of knew this because we knew that acceleration was the slope of a velocity versus time graph. So we'd say, okay, delta v over delta t is equal to a. So delta v is equal to a delta t, or v minus v naught equals a delta t, or v equals v naught plus a delta t, where I've replaced just the delta t with t, because again, usually we start from time 0. Let's plug that equation into our velocity versus time graph. Again, our equation is v equals v naught plus at. Let's make a velocity versus time graph from that. I have v equals v naught plus at, so I started at v naught. I have a slope of a, so my slope is a. That's the big thing here. My slope is a. Or, well, what's the difference between my final velocity and initial velocity? Well, that's just v minus v naught. So I can figure out my displacement, again, by taking the area under this graph. So the area under the graph, this is a trapezoid. Now remember, the area of a trapezoid is base times average height, but this time it's actually more useful to think of our trapezoid as the sum of a rectangle and a triangle. So, well, okay, what about my rectangle? The rectangle is the bottom area, so that's going to be base times height, or base is t, height is v naught. So rearranging, we have bottom area is v naught times t. What about the top area? Well, the top area is the area of a triangle, but the area of a triangle is 1/2 base times height. The base is still t, the height is v minus v naught. But remember from the last slide, taking the area under that acceleration versus time graph, we got that v minus v naught, that is delta v, was equal to a times t. Well, here v minus v naught is my height. I'm going to replace that with a times t. So that's where we get that the top area is 1/2 at squared. So if you drop an object from rest over a cliff and neglect air resistance, you see that the distance traveled is going to be proportional to time squared. So that's a really big deal, the fact that it's undergoing constant acceleration. So constant acceleration can result in a large change in position when aggregated over a large period of time. So adding these up to give you the total area for some initial velocity, delta x, the displacement that is, well, bottom rectangle plus top triangle, v naught times t plus 1/2 at squared. That's what our displacement is. And again, all we did was we took the area under a velocity versus time graph and then used the fact that v minus v naught is called AT. So again, it's a good idea to memorize all of these equations. Even if you are going to be allowed to use a note card or something like that, you should still memorize them, because when you actually need to apply them to solve word problems, if you have them memorized, it's more likely that the correct equations are going to be at the top of your mind. In other words, you're going to come across a problem and immediately recognize, oh, I need to use this equation. The quicker you memorize the equations, the quicker that's going to happen. Now, let me show you some cool math that you don't need to memorize. So for this slide and the next slide, we're going to temporarily assume that acceleration is not constant, but we will assume that jerk is constant. So we'll say, okay, we have some constant jerk. Well, in that case, take the area under a jerk versus time graph. That's change in acceleration. Well, that area is base times height, so time times jerk. So apparently delta A is JT, so A equals A naught plus JT. And then graph that the same way that we just did, and you get that the area under your velocity versus time graph would be A naught T plus 1/2 JT squared. And that's delta V. So V equals V naught plus A naught T plus 1/2 JT squared. So from there, you could find the area under this parabola. There are formulas for finding the area under a parabola. I believe that Pythagoras was one of the, sorry, not Pythagoras, but Archimedes was one of the early people to derive a formula for the area under a parabola on a graph. And upon applying that formula here, you would find that the displacement is V naught T plus 1/2 A naught T squared plus 1/6 JT cubed. I'm not going to show that proof. It's a lot easier using calculus. In fact, a lot of things turn out to be a lot easier using calculus. But in any case, this is not a calc-based class, so we're not going to do that. But those of you who have some calculus experience might actually recognize this as the first 4 terms of a Taylor series expansion. But in any case, again, you do not need to memorize these equations. You don't even need to know them. I'm just showing you that the same procedure that we just used can be extended to other situations. Now, how do we solve problems? First, we identify our givens, and we figure out which of the equations contains all of the givens, including the unknown. Now, when I say all the givens, what I really mean here is which of the equations that we've memorized includes the unknown and has every single one of its other quantities listed among our givens. That's really what I mean. So look for an equation that has your unknown and make sure that all of the other quantities in that equation are listed in your givens. And sometimes you might find it easier to use more than one equation. In fact, sometimes in multi-step problems, you'll have to. And then use the equation, plug in the givens, and solve for the unknown quantity. Now, a lot of times it's going to be better to manipulate the equation to solve for the variable first, and then plug in your givens. How you do it is up to you. We'll actually do it both ways. The mathematically sound way of doing this often is to solve for the variable first, and then plug in your givens. But again, we'll do it both ways. So, a lot of times when we're trying to identify givens, we look for fundamental units. Like we know that velocity units need to have units of position over units of time. And then other things like clue words. For example, stop. For example, if it starts from a stop, that means V naught is equal to 0. Or it comes to a stop, that means V is equal to 0. Rest implies that it's either V naught or V was equal to 0, depending on the rest of the words in the problem. Drop, to say that you drop an object, implies that the initial velocity is equal to 0 and the acceleration is 9.80 meters per square second downward. Now, if we're assuming up is positive, then that would mean that we would need a negative in front of our acceleration. Though for non-AP physics, we're often going to recommend that we simply say that our acceleration has, or we're simply going to say that the direction that is positive is going to be the direction of our initial velocity in most of our problems. Free fall, again, implies that the acceleration is 9.80 meters per square second in the downward direction. I highly recommend memorizing this number. because it's a special number, as we're about to see. Now again, traditionally, up is positive and toward the right is positive, but a lot of times, as I've mentioned before, it's wiser to pick the positive direction as the direction of the initial velocity, because that'll often either reduce or eliminate confusion involving double and triple negatives that might otherwise show up when we're solving our problems. So let's look at some examples of writing givens. Let's say we have an angry mob catching up to a physics teacher after receiving their grades. How ironic. They throw the physics teacher off a tall building, and the physics teacher is thrown straight down with a velocity of 20 meters per second, and the teacher falls for 3 seconds before landing on a stack of empty cardboard boxes. If you're asked from how high was he thrown, well, what are the givens? Well, there's one. There's another one. There's another one. Ooh, throwing the physics teacher off a tall building. That means it's in free fall. And from how high? That means we're interested in either x or x naught, depending how we're thinking about the problem. So, givens, well, there's the time, 3 seconds, initial velocity, and again here we're making down positive, so v naught is, we're calling it plus 20 meters per second, and therefore the acceleration would be plus 9.8 meters per square second. Again, we're assuming that down is positive. From how high was he thrown? Well, here we're saying that x naught is 0, and x, the final x, is what we're after. In other words, what we're really looking for is delta x. So, there's your list. How about this next one? Baseball is thrown horizontally at 45 meters per second. That's pretty fast. It's like 100 miles an hour. Slows down at a rate of 5 meters per square second. How long is the ball in the air before coming to a rest? Assuming that this continues to last, which of course is not reasonable, but whatever. Well, here's our initial velocity. Ooh, those look like acceleration units. Distance units over 2 powers of time units. Those are acceleration units. How long is the ball in the air? Oh, that's time, and that's what we're looking for before coming to a rest, so apparently v is equal to 0. Now notice that since I'm calling my initial velocity positive, it's slowing down. That means the acceleration must be negative if we're calling the initial velocity positive. Now, if we were calling the initial velocity negative, then the acceleration would have to be positive. The whole point is that whenever something is slowing down, the sign of acceleration is opposite the sign of velocity. And the final velocity is 0. And we're saying that we started at 0. We're wondering how much time it takes. So that's what your list should look like in this situation. So now how do we solve these problems? Let's consider a monkey sliding a banana at constant speed of 4.62 meters per second over a smooth surface for 5.32 seconds. How far has the banana gone after the end of that time? Okay, well, let's identify the givens. Well, it says it's a constant speed, and since we're working in one dimension, we're going to figure that that means a constant velocity, which means the acceleration is 0. So v naught is given, time is given, we're asked how far it went. Delta x equals question mark. So, well, let's see now. Which equation has my unknown, that is delta x, or at least x, and has all of the other quantities listed in the givens? I can actually think of 2 equations that work here. The easiest one is going to be thinking, okay, just think of the equations in order. That's going to be delta x equals v naught t plus 1/2 at squared. The reason this is the easiest one here is because the acceleration is 0, so we can immediately eliminate the 1/2 at squared part. Now another equation that would work would be the right side of the v average equation. Delta x over delta t equals v naught plus v over 2. Well, if the velocity is constant, v naught and v are the same, so v naught plus v over 2 is just v naught. So, because v naught plus v would just be 2v naught, so the 2's cancel. So, either way, we end up coming to this. And we're asked how far the banana's gone. So we have delta x equals v naught times t being left over. So you plug in the numbers, and you get 24.6 seconds. And again, notice that by plugging in our units, you got to plug in your units when you plug in your numbers, the seconds cancels, leaving us with units of meters. The units go along in the math just like the numbers. And if we screwed up with our equation, then there's a chance that we might end up getting wrong units on our answer. Like if we thought, oh, maybe it's V0 divided by t. Well, that would end up with units of meters per square second. Well, we know that those aren't units of position. In other words, plugging in units also provides a reality check. How about this problem? How long does it take an F-15 fighter to fly 3,000 miles across the U.S. if it's flying at 600 meters per second in a constant direction? So here's our F-15, which is a really awesome fighter plane. Even though they come out of the 70s, they're still some of the best fighter planes in the world. So, well, let's see. Since it's a constant rate, that means A is equal to 0, no acceleration, which means V and V0, initial or final and initial velocities, are the same. And we're wondering about the time. And we're given the distance, that's 3,000 miles. But remember, we got to convert things to SI units. So miles to feet, feet to inches, inches to centimeters, and then centimeters to meters. So there's our delta x. I was being a bit of a nerd and decided not to do any rounding here. In general, you shouldn't round until the end, but it's okay if you write down non-rounded results. Just make sure that when you're using your calculator, you plug in non-rounded results. But writing things down kind of in the middle, you can either plug in a non-rounded result or a rounded result. But when you actually plug it into your calculator as opposed to just writing it down, make sure to plug in non-rounded results. So this will be the number that we plug in our calculator for delta x. So delta x is v0 t plus a half at squared. So that's the same as this equation, just moving the x0 to the other side. But here we really care about delta x anyway. So delta x is v0 times t. They're asking us for t though, so I'm going to divide both sides by v0 and be a good physics student and solve for my variable first, and then plug in my numbers. Plugging in numbers gives 8,046 seconds, which, just pretending that these numbers are supposedly good to 3 sig figs, which they're not, but whatever, is 8,050 seconds. So that's a little over 2 hours. 3,600 seconds per hour, so 7,200 seconds would be 2 hours. So that's pretty good to get across the United States in 2 hours. If you've ever been on an airplane across the United States, you know that it generally takes a lot longer than that. Okay, so now let's look at another problem. An arrow leaves a bow at 42 meters per second, and its velocity is reduced to 34 meters per second by the time it hits its target. How much distance did the arrow travel if it was in the air for 2.4 seconds? Well, again, we write our givens first. Writing our givens is not only good practice in terms of like making it easier for people to grade things, but it can also often help you to realize what equation you should use. So basically we're looking for either final position or displacement either way, since x0 is 0. So we need an equation that has delta x or x in it, and everything else in that equation is listed in the givens. So, well, let's see. Delta x equals v0 t plus 1/2 at squared. Oh, that doesn't work because a is not in our givens. How about v equals v0 plus at? Well, that's silly. The unknown isn't even in our givens. What about v squared equals v0 squared plus 2a delta x? Well, no. Again, acceleration is not in our givens. How about the v average formula? Delta x over delta t equals v0 plus v over 2. Ah, in that case, everything is in our givens. Delta x is what we're looking for. Delta t or t is in our givens. v0 and v are also both in our givens. So that's the equation we want to use. So the first three, again, can be eliminated because they either have something that isn't in our givens or they just don't have what we need. So finally, we realize it's the fourth equation. So we use that, and we plug in our numbers. And upon doing that, we find that x is 91.2 meters. That's actually about the length of a football field. 91 meters is about 100 yards. So there we go. That's how we solve these types of kinematics problems. So consider another problem. At a drag race, a jet car travels 1/4 of a mile in 5.2 seconds, and we're rounding a quarter of a mile to 402 meters. Yeah, I know it's a little bit longer than that. What is the final speed of the car and its acceleration? So, well, it's a drag race, and the idea is that it starts from rest. And the displacement is 402 meters. And this happens over a time of 5.2 seconds. So what's the final speed? And what's the acceleration? So again, this is a problem where we don't have acceleration listed, so we must use an equation that doesn't have acceleration in it. That's another clue to thinking about what equation you should use. Think about the quantities that are not listed in the problem. If you can see the quantity that is not listed in the problem, and that's also not the one being asked for, then you want to say, okay, I need to find the equation that doesn't have that quantity. So we realize, oh, acceleration is not given. There's only one equation that doesn't have acceleration in it. That's the right side of the v average equation. Delta x over delta t is v naught plus v over 2. Plugging in our numbers, we solve for the final velocity of 154.61 meters per second. That rounds to about 155 meters per second. That's, I don't know, maybe about 330, 340 miles an hour. So it's pretty fast. What about the acceleration? Well, the acceleration can be found from the delta x equation. Or you could use the v equals v naught plus at equation. Or you could use the v squared equation. Because essentially, by finding the distance now, finding the final speed, that makes several equations redundant now. So, in any case, we can solve for the acceleration using any of a number of equations, and either way you get 29.73 meters per square second. How does that compare with the acceleration due to gravity that we've talked about already, the acceleration of a falling object? Well, that's actually a unit. G is a unit. It's the symbol for the acceleration of a falling object in Earth's typical gravitational field, 9.80 meters per square second. So, well, we can do a unit conversion, therefore. 29.73 meters per square second times 1g over 9.8 meters per square second turns out to be 3.0 g's. G's! Now, before we examine these funny g units more closely, let's take a look at a problem with a cheetah. So a cheetah can run from 0 to 70 miles per hour in 2.2 seconds. So part A of this is just converting everything to SI units. So 70 miles per hour turns into 31.29 meters per second. Part B, though, what is the cheetah's acceleration in meters per square second? Well, let's see now. We're wondering about what the acceleration is. We're told initial velocity, we're told the final velocity, we're told the time. So what we're not told is how far the cheetah went. So we need an equation that does not have x or delta x in it. Can you think of such an equation? How about v equals v naught plus at? That's the equation that we're going to need here. This is the only one of our basic kinematics formulas that does not have delta x in it. So since the problem doesn't have delta x listed anywhere, including in the unknown, we want to use this equation. So plugging in numbers, we get that the acceleration is 14.22 meters per square second. So if you were being required to show your work, in addition to probably getting a check for listing your givens, you have a check for the equation, you have a check for plugging in your numbers with units, you have a check for the magnitude, or at least the numerical value of the final answer in SI units, and you have a check for showing the units as well. What about the cheetah's average velocity? Well, we have an equation for that. We'll just directly plug it in. So, in miles per hour, that's real easy. Just take the 70 and divide by 2 since it started from rest. Or, well, even in meters per second. Take the 31.29 and divide by 2 because, again, it started from rest. If it didn't start from rest, if it started from some other speed, you would plug in that other speed in place of the 0 right here. So, like if the cheetah started from 30 miles per hour and accelerated to 70 miles per hour, then the average speed would be 50 miles per hour. So how much distance did the cheetah cover in that 2.2 seconds of going from 0 to 70? Well, we can use any of a number of equations for that because now we know the acceleration. So let's just use an easy one, the V average equation. Delta x over delta t is v naught plus v over 2. So solve for x, and you get 34.42 meters. So looking at another example, consider a car going from 0 to 60 in 8.5 seconds. What's the car's top speed in meters per second? What's its acceleration? Well, converting 60 miles per hour to meters per second, get 26.82 meters per second. And to find the acceleration, that's where we have to solve an equation. So again, we're not told any distance, so we're going to use the v equals v naught plus at equation and solve for acceleration and get 3.16 meters per square second. So now let's look at these funny acceleration units, g's, in more detail. So we often hear it stated as a force factor. So it's like it describes how many times the force of or acceleration due to gravity acts. So 1g, even though we talk about it as a force factor, g's have units of acceleration. It's just that something that we're going to get to in the next unit, this connection between force and acceleration, we could also think of it kind of as a force factor for something of a given mass. So something experiencing an acceleration of 2g's would have an acceleration of 2 times 9.8 meters per square second, because again, g is 9.8 meters per square second. All you're doing is you're doing 2 times g, where little g is the symbol for the acceleration due to gravity, the acceleration of an object in free fall near Earth's surface, which is 9.80 meters per square second. So 4g's would be 4 times 9.8, which turns out to be 39.2 meters per square second. Now, keep in mind that since it's not an SI unit, you're usually not going to be able to apply formulas of g's unless, quantities that are given in units of g's into your equations, unless you know that the units cancel. There will be such situations later on in the course. But generally speaking, you're going to need to convert to meters per square second before using them in our formulas, especially our kinematics formulas. So, quick question. A car decelerates from 26 meters per second to a stop. The car and passengers experience a deceleration of 1.5 g's. How much time did this motion take? Well, you have your givens. Initial velocity is 26 meters per second. Final velocity is 0 because it says it came to a stop. And since it's slowing down, that means that since we're calling our velocity positive, the acceleration must be negative. Remember, when things are speeding up, the acceleration and the velocity have the same sign. When things are slowing down, acceleration and velocity have opposite signs. So, well, that means acceleration is minus 1.5 g. But we need to convert that. Well, a g is 9.8 meters per square second. So minus 1.5 g's is minus 14.7 meters per square second. So again, in this equation, the v equals v naught plus at equation comes to our rescue. So plug in v naught, plug in a, note that negative sign, and solve for the time. Time is 1.77 seconds. If you had forgotten about your negative sign, if you were being negligent, then you would have ended up getting a negative time, which would have been nonsensical. So we've covered a lot here. We've shown how you get the basic algebraic kinematics equations. We've shown how you can identify givens from various word problems based on not only the language of the problems, but also the units involved in the problems. And then we've gone through how to use the equations to solve problems and end up getting solutions to potentially real-world scenarios. In the next discussions, we're going to examine how to apply this to certain representative types of situations. Situations where two objects are racing next to each other, or at least along the same direction of motion, and situations where the acceleration changes. Wait a second, I thought we said the acceleration didn't change. Yeah, so in other words, it's situations where you have a constant acceleration, and then something happens, and then you have a different constant acceleration. So, I'll see you all then. Thank you for watching.